little bit. Still looking at exponential functions, okay, but we're going to look a bit more of exponentials, down the side here. Now you don't know how to work out the differentials yet because we're looking at gradients, so obviously we want the differential of them. So I've worked them out for you. So if we have a look at this first one, so I've got the function y equals 1x, which we should know what that looks at from last lesson's work. And the differential of that is just 0. Okay. Then if we look at the next one, y equals 1.5 to the x, y equals 210, 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 y equals 2 to the x. Again, blue is the original function and red is the gradient. Then we go to 2.5 to the x. Okay. Now what we should hopefully notice is if I just go back to 1.5 to the x, okay, and then 2 to the x, and 2.5 to the x, and if we just put in 3 and then 3.5, we can see that the red and the blue lines get very, very close together and then pass each other. So if we're talking about our functions and our gradient functions, and we've sketched them, in between 2.5 and 3, we may have a point where our function and our gradient function are exactly the same. Okay, and this is really important. So this is where something called E comes in. Now, some of you will know about E, some of you may not do. Okay, so E is around 2.7 and it is known as Euler's number. Okay, now E is very 2 e to the x. So this little bit here is really, really important. Please make sure we note it down because it will come in real handy later on. So we have exponentials and then we have something called the exponential function, and that is e to the x. Okay, you do have it on your calculators, so it is a location. You can locate it. The first thing we need to be able to do is we need to be able to differentiate our exponential functions. Okay, now we're going to focus on y equals e to the kx, okay, where k is just a number, and when we differentiate y equals e to the kx, our differential to y dx will become k e to the kx. Okay, just be careful. This isn't just a standalone rule. It is part of something called the chain rule, which we do next year. Okay, which can obviously be applied to all sorts of other functions. So all we need to really notice is whatever our constant is with x is going to get dropped down and multiplied by whatever our coefficient of e is. Okay, so just some quick examples. If if we've got e to the 5x, when we differentiate with respect to x, we get 5e to the 5x. The 5 just gets multiplied down. E to the minus x is effectively e to the minus 1x. Drop that down. We'll give with, just be careful with, 4e to the 3x. We drop the 3 down as a multiple, so we will get 12e to the 3x. So our amount of x in our power will not change. Okay, it is just the coefficient in front that will. Okay, you need to be really, really careful. Okay, make sure we understand where that comes from. Right, pause the video quickly, have a go at those 3 for me, and then we will go through them nice and quickly. Okay guys, right, let's have a look. So e to the 2x, we should drop the 2 down as a multiplier, so we will end up with 2e to the 2x. E to the minus 3x, we drop the negative 3 down, so we'll have minus 3e to the minus 3x. And the last one, drop the half down as a multiplier, so we'll end up with 1e to the 0.5x. Okay, or just e to the 0.5x, whichever way you need to put it. Okay. nice and simple, differentiating e to the kx. Okay, or a e to the kx, as we did with some of these. Okay, right. Bit of transformations of graphs with e to the x. Nothing any different from what you were doing last lesson. We just x. We know what 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 e to the x looks like. Exactly the same. X. Exactly the same. X. Exactly the same. X. Exactly the same as what we did last lesson. Just means our rate of change is quicker. Okay, it's a steeper gradient. It's a steeper rate of change. So we have stretched by a scale factor of a third on the x-axis, so we've got that sharper incline. 5e to the minus x. Again, guys, you can always check these by plugging values of x in to see what you get out. Okay, it is, because it's a negative x power, it is going to be a rate of decay rather than an exponential growth. And obviously 5e to the minus x, again, is going to go down a lot sharper than e to the minus x. Okay, the last one, 2 plus e to the third x. So we've got two parts to this. You need to sort the e to the third x out first. So we stretch by a scale factor of 3 on the x-axis, so it's just going to be elongated a little bit. Okay, and then we have a translation line up to. What you need to be really careful with is these asymptotes. So the asymptotes that are down here, normally, okay, at x equaling y equaling 0 even on the x-axis, because we have translated up by 2, that asymptote has gone up by 2. You have to make sure you put that on. Remember, guys, these are still sketches. We have to put all our key bits of information on. That includes intercepts, that includes roots, that includes asymptotes. So please, please, please be really, really careful with that. Make sure you do your stretching, then you put your translation on afterwards. You do have to work out what your intercept is. In this case, it's nice and simple because we've just translated up to give us the 3. Exactly the same as what you've just been doing. Okay, we're just using e to the x instead. Okay, right, again, can we pause please and have a go at those two? Okay, e to the 2x shouldn't be too difficult. Okay, e to the 2x, all we're going to do, compare it to e to the x. We stretched parallel to the x-axis by a half, okay, which just means we've shrunk everything down so it's a much steeper gradient. E to the minus 2x to the minus 1. We've got a negative power, so we're going to have a rate of decay rather than a rate of growth, okay, and because we've shifted down 1, our asymptote becomes y equals minus 1, and our intercept that's gone from 1 will now go to 0 instead. So make sure you've got everything on that you need to. Okay. Just a couple of new things, guys, with regards to this. You've got your differential of e to the kx is k to the kx. Okay, and you just got to make sure you know that is wrong. That is really, really important to what we look at for a little bit this year and especially next year. And then transformations of e to the x, exactly the same as our other exponentials from last lesson. We are just using e to the x instead. Okay, right. Can you look back on Show My Homework for me and have a look at what questions I would like you to do from exercise 14b?